Welcome to this session on the reactivity of alkyl halides towards nucleophilic substitution reactions. In this lesson, we will carefully analyze how different types of alkyl halides behave under two important mechanisms, the SN1 mechanism and the SN2 mechanism. By the end, you will be able to explain why reactivity differs across primary, secondary, and tertiary halides, and understand the detailed mechanism of alkaline hydrolysis of methyl bromide. Let us first compare the reactivity orders. In the SN1 mechanism, the rate of reaction is fastest with tertiary alkyl halides, followed by secondary, then primary, and finally methyl halides, which react the slowest. This is because SN1 reactions proceed through carbocation intermediates and tertiary carbocations are the most stable. On the other hand, the SN2 mechanism shows the exact opposite trend. Here, methyl halides are the most reactive, followed by primary and secondary halides, while tertiary halides react the slowest. This is due to steric hindrance, which makes backside attack by the nucleophile increasingly difficult as the size of the alkyl group increases. Now, let us focus on a specific question often asked in examinations. Explain the SN2 mechanism, or more specifically, the mechanism of alkaline hydrolysis of methyl bromide, also called bromomethane. And this is an ideal example because it highlights the features of the SN2 pathway very clearly. Before going deeper, let us break down the meaning of SN2. The letter S stands for substitution, indicating that one group in the molecule is replaced by another. The letter N represents nucleophilic, showing that the attacking species is a nucleophile. Finally, the number 2 indicates that the reaction is bimolecular, meaning the rate of reaction depends on the concentration of both the substrate and the nucleophile. In alkaline hydrolysis, when methyl bromide is boiled with aqueous potassium hydroxide, it undergoes hydrolysis to form methanol and potassium bromide as a byproduct. In ionic form, the hydroxide ion attacks the carbon atom of methyl bromide, displacing the bromide ion. The overall reaction is simple, yet the way it proceeds gives us deep insight into the SN2 mechanism. Written in ionic form, the reaction looks like this. Methyl bromide reacts with hydroxide ion to form methanol and bromide ion. Notice that the potassium ion remains unchanged and acts as a spectator ion. By cancelling common ions, we highlight the essential substitution step, the nucleophilic attack of OH- replacing the leaving group Br-. The rate of this reaction depends on the concentration of both reactants, the substrate and the nucleophile. Mathematically, the rate is directly proportional to the concentration of methyl bromide as well as hydroxide ions. This is the hallmark of a bimolecular reaction and is the reason why the reaction is called SN2. The SN2 mechanism takes place in a single concerted step. The hydroxide ion attacks the carbon atom from the backside, exactly opposite to the leaving bromine atom. This leads to the formation of a highly unstable transition state, where the carbon is simultaneously bonded to both the nucleophile and the leaving group. Finally, the bromide ion departs and methanol is formed. Importantly, this backside attack causes complete inversion of configuration at the carbon atom, often called the Walden inversion. To visualize the process better, we look at the energy profile diagram of the reaction. On the y-axis, we have potential energy, while the x-axis shows the progress of the reaction. The reactants, methyl bromide and hydroxide ion, must cross an energy barrier to reach the transition state. This energy barrier is called the activation energy. Once the transition state is formed, the products, methanol and bromide ion, are released with a drop in energy. The overall reaction is exothermic, which means it releases energy indicated by a negative heat of reaction. The single energy peak confirms that the SN2 mechanism proceeds in just one step.